Okay, let's continue with the lecture of limits at infinity or infinite limits. Okay, so well, infinite limit was something that we computed already. Let me go here. Well, we discussed also this rule when we have ratios of polynomial or rational functions. Okay, so let me just mention, just to finish this section, a couple of examples that I include in your lecture. Okay, so here we have a rational function. You might say, well, I have here this square, okay. But what we have within the square is a polynomial function, so we are still considering a rational function. So I took this example also from some of the exercise in your textbook. And what I did, I plot or graph the function, okay, using this application that is called Desmos. Just to illustrate for this lecture what is going on with this particular function. What they say in the exercise is just to compute the limit when the independent variables go to infinity. In other words, the limit at infinity. Okay, so if you look at the graph and you consider either very large positive number or very large negative number, or negative number that in magnitude grows and grows more anytime, you can see that in the graph, the branch that represents, or the curve that represents this function are going to be limited by this horizontal line that is y equals to 4/9. So in that case, we have that the limit of the function either goes to negative infinity or positive infinity is going to be 4/9. So that limit is a limit at infinity. In here, in between, you see that we don't have any curve between those values, and the reason for that is why around this interval, well, the function here, this square, is going to be negative, and that is the reason that the function is not defined there. But it's not that is not part of the exercise. The exercise is just to compute the limit. Now the point is, okay, what I can do in order to compute the limit. Okay, I'm going to give you the tips to solve this exercise. I will give you the steps. So what I want you guys to do is go by yourself, try to compute the limit, and try to make sure to get this value of 4/9. So I'm going to give you the tips how to do it. Okay, so you have here this. This is 2x to the 4, okay? And then you have minus, and you have this one over here. That is the square root of 4x to the 8th power minus 9x to the 4th power. Whenever you have expression like this that involves two terms, and you have a negative symbol in between, okay, try to multiply by the conjugate of the expression. For instance, okay, let me just go in detail here. So let's assume that this term is A, and let's assume that this other term is going to be B. What you have here in the denominator is A minus B. What I'm telling to you is to do the following. Multiply the denominator and the numerator by the corresponding conjugate of this. That is going to be A plus B. Okay? So you're going to go here into the expression, and then you're going to multiply the denominator by this one, A plus B, and then A plus B. And make the corresponding simplification. What is going to be A plus B? A plus B is going to be 2x4 now plus all this square root 4x to the 8 and minus 9s4. So you are going to multiply all of this expression by this one. But if you do that in the denominator, you need to do that exactly in the numerator. Now, what is going to happen when you make that multiplication in the denominator? Let me put here number 2. This is step number 1. Step number 2. What is going to happen in there? Well, what is this? This is a difference of a square. This is the square of the first minus the square of the second. Okay? You're going to have the square of the first, which is going to be the square of all this expression here. That is going to be 4x to the 8th power. Okay? And then you're going to have minus the square of the second, which is the square of all of this. If you square all this expression, what is going to happen? You're going to cancel the square root symbol, and you're going to have x 4x to the 8th power minus 9x4. You're going to have that in the denominator, in the equivalent expression that you are deriving. Well, look at here. This go with this one, and then in the denominator is going to leave only 9x4. Of course, you need to check what you're going to get in the numerator. Then, in a third step, you're going to remove this s squared. What is going to do? In the corresponding rational expression that you're going to get, multiply by s squared and divide at the same time by s squared. That's what they mention in your textbook, okay? When you have a rational expression that are polynomials, divide every term in the numerator and the denominator by the maximum power of the denominator. In this case, the denominator is going to be something like that. When you divide 9s squared by, s to the 4th power by s to the 4th power, then in the denominator, you're going to have 9. If you do the corresponding simplification in the numerator, what you're going to get at the end is going to be 4. So that 9 is coming from there, and 4 is something that you need to compute by yourself in your simplification. Okay, that's the way to go. So those are the steps that you need to follow. What happened? In the notes, I put as an exercise all these examples, and then I'm going to give you some time that you do by yourselves, and let's say this coming Saturday or Sunday, I will give you the detail. I will give you the detail of what I'm explaining here. But that's the way to go in here. So those are some tips on how to deal with this exercise. Another exercise that I want to comment to you is when you have an slant asymptote for a given function. In a rational function, when is going to happen that? When the degree of the numerator is greater than the degree of the denominator, but only for one unit. Okay? So in that case, the limit at infinity is going to be infinity, and the limit at negative infinity is going to be negative infinity, but it's going to be bounded by some specific linear function, and you need to describe that linear function. Okay? The linear function in here, again, I use Desmos just to show you the response. The linear function is this dashed line in green. You can see that when the x values goes to infinity, very large positive number, the function that is here in red goes also to infinity, but is limited by this dashed line in green. Exactly the same with the negative number. If I go with a very large number in magnitude but negative, the function goes also to negative infinity, but it's going to be limited by this linear function in here. And that linear function is what we call the slant asymptote. What is that asymptote? That asymptote is y equals to x minus 6. Okay? Now, the question is the following. How I derive the expression for this slant asymptote? Well, what you need to perform is, for this particular case, synthetic division. Synthetic division. The division between two polynomials, but in this particular case, the denominator is of this form, x minus a number. In this case, is s plus 6, that can be written as s minus 6. Okay, so it's in this form. When you have a division of polynomial in which the denominator is a binomial with a leading coefficient equals to 1 and independent term, then you perform a synthetic division. How do you perform the synthetic division? Please review the module that I create that is called Review of Collage Algebra. In that one, I explained there. Okay? If you have another type of polynomial, okay, then make a full or what is called long polynomial division. So you need to review that. You need to remember that from collage algebra. And when you make this, either in this case or in this case, when you perform the division, then is when you're gonna get the SLAM asymptote. Okay, so again, in the nose, you're gonna have as a equation to derive that SLAM asymptote following the tips that I'm giving to you at this moment. I will give you some time so you can do it by yourself, but on Saturday, on Saturday or Sunday, I'm going to post all the details. So in that case, you're gonna have you will have all the details. So with all the breakdowns, so you can use that one in order to make your exercise, if that is the case that you find an exercise that is in this way. By the way, this function is not defined in S equal to -6. So at this point in S equal to -6, we have a vertical asymptote. So that's why the function goes to infinity, and in the other side, the function goes to -infinity. But that is something that has to do with the previous section. Okay? Perfect. Before finish this part, I mentioned about nodes. Okay? Let me just open here. Okay, let me go to, here is D12 in our course. Let me go to our module number 1, which is limits. And I was, as I was mentioning during the video, you're gonna find here something that is called limit second part nodes. Okay, so let's open this. This is the document that I was making reference during the videos. Okay, so you will see some practice exercise. 1, 2, 3, 4, 5. There are 5 practice exercises that are basically to make the detail of those examples that I showed you in the previous videos. For instance, the first one is within the lecture number 2 in D12 at the example of infinite limit, page number 5, factor the polynomial. So let me open that document over here. So in page number 5, which is this one, page number 5, let's factor this polynomial. That's what I'm telling to you over here. X squared minus 2s minus 3. So let's factor this. So we're gonna cover the detail with that lecture's note. Okay, so let's move forward. In the next one, I say, okay, for the example of aim behavior and asymptotes of rational function, page 16, simplify the given function and show that the horizontal asymptote is y equals to 4/9. What is that one? That one is this one. Is this one that we were talking about. So, in other words, compute the limit at infinity of this given function. So, follow the tips that I gave you during the video and then make this practice exercise over here. Show all the details. Okay? You don't need to turn that to me. That is for your practice. Just to fix procedures of how to make calculations or computation of limits when you have rational functions. Okay? Remember, I'm going to give you some detail. I'm going to give you some time between today and tomorrow, and then on Sunday I'm going to show you all the details. But don't wait until I give you the details. Make your effort, okay? Try to make by yourself the exercise, and if you are not able to get it, write an email to me asking me some details, so I will be more than happy to provide you with those details, or wait until Sunday to see how you can proceed. But save time and do by yourself. Okay, exactly the same with the other one. Let me see what is the other one. In here, okay, for instance, for the sample of the slant asymptote on page 70, okay, try to show that y equal to s minus is this corresponding slant asymptote. So T performs synthetic division of rational expression. That's what I tell you in here for this particular example. And some more. We have another video. We're going to have another video about continuity in which we're going to have some additional practice exercise. Okay? Well, what else I want to tell you in here? Okay, what I want to tell you in here, in addition, is that the notes for the first part of limits, the keys, is already available to you guys. I put that one in yesterday or before yesterday. If you open here, that is the notes, but now you're going to have the breakdown for each one of the exercise that I suggest, the practice exercise. Okay? So what you need to do with the second one? With the second one, exactly the same. Okay? Go by yourself, and the reason for that is that you're going to look at the video of your lecture, you review your lecture, you review your textbook, and then you make this practice exercise just to fit the what you are learning. Then you can go with your homework and so on. Okay? Well, thank you.